In this problem, we want to understand the motion of the point in A with respect to ground as it moves in absolute motion. Here we can define a global frame of reference such that we have a fixed frame here that we call N, and then we try to describe the position of the point from the origin with respect to the global reference frame. To do so, we can create a horizontal vector here that goes from the origin to the point B. You can see that that vector that I will call R1 has direction in the x hat axis in the negative direction, so it's negative in x hat. Then we can create a vector from B to the intersection between the two bars, and you can see that that vector that I will call R2 has a magnitude of 2b, and its direction is inclined in an angle theta with respect to the horizontal axis, or x hat. Then we can create a vector from this point to the next joint, which has magnitude b, and the direction also relates to the same angle theta, which we will see later. I will call this vector R3. And finally, we can write a vector that goes from this point to our point of interest, and I will call this vector R4. And that vector has a magnitude of b, and the direction is also related with theta. If we add R1 plus R2 plus R3 plus R4, we are able to go from the origin O to our point of interest in A. So this vector is describing the motion of A, and I will call that vector RA. Since we are interested in describing the velocity of point B in terms of the variables theta and v, we can tell that the position of the point B is related with vector R1 directly, and the velocity or the position of point A is related to RA, so its velocity is the derivative of the RA vector. And we can use this equation to relate our variables and describe VA and VB with respect to the variable theta and be able to solve the problem. Now let's look at the relation between the angles of all the vectors that I just described. First, let's look at the drawing, at the blank drawing here, and observe that this angle theta here, if we draw a horizontal line here, you can see that the angle theta is the same angle theta here, and it's also the same angle here too, since the horizontal line divides this angle here in two equal parts. If we apply the same logic, the same reasoning for the second horizontal line, you can also see that the angle theta is also the same angle here, and then also the same angle here. So from our previous drawing that we defined, where we defined the vectors, you can see that all the vectors are 2 and R3 and R4 their directions are defined by theta. Now let's do the description of this problem using Python. I will move the window here and have the drawing here so that we can see both. And I'll do my imports first. And now let's create the reference frames. We start with our global reference frame n, and then we want to have a reference frame with a positive rotation on theta of theta radians, so that it aligns with the bars that point up, like this one and this one, so R2 and R4. This is our x hat for the reference frame. Let's call that reference frame A, and this will be our y hat for reference frame A. And then you can see that the angle between the horizontal and axis and the x hat axis of A is theta, so that we write n dot orient new. So we orient a new reference frame from n. We call this new reference frame A. We orient by axis, and we want to rotate theta degrees around the NC axis. And we store that reference frame in the variable A. We have not defined theta yet, so we have to define it by using dynamic symbols. And you can see that we have our variable A. If we write a dot x, we are describing this vector, and you can see that ax expressed in the n frame of reference corresponds to cosine theta in x and sine theta in y, meaning that we are computing the components of this vector in the horizontal and vertical axis of the n frame reference frame. And we can do the same for a frame of a reference frame that it's rotated negatively, so something that goes down. Also a rotation of theta, so we use the same variable. We will call this frame B, and you can again observe that the relation between B and N is also the angle theta, and we choose this frame of reference so that the BX axis aligns with our vectors R3 and just R3. Let's continue with the code. We will do another line for vector V. This one has a rotation of minus theta because we are rotating in the opposite direction, and we can observe the vector B expressed in n, and you can see that there is a negative sign for the y component, so that the x hat vector points downwards on the vertical axis, which makes sense with our choice of reference frames. Now let's try to write the vectors R1, R2, R3, and R4, which are necessary for describing our problem kinematics, and I'll arrive to the equations that we need to use to relate the position of point B with respect to changes in point A. Let's start with R1. R1 is in the direction of the x hat of the global reference frame, on the negative axis, so it's minus nx, and it has a magnitude that we don't know yet because it's the distance from the origin to our point B, so it's this unknown distance. Let me clear the clutter here by removing one of the layers that we're not using, this one, and you can see that we have a distance here that represents how far our point B is from our origin. Let's go back to our layers, and so that we have the frames that we need, and then we need to define a variable for that distance. I'm choosing x for the variable, so I now need to add another dynamic variable because x changes in time. We have theta and x as our new dynamic symbols, and we have the definition of R1 as negative x in the direction of x hat, global x hat. Now let's do R2, and that's 2 times b. R2 is this vector here, and remember that R2 is this vector, so 2 times b. We still don't have b, we don't have b yet, so let's do a definition for b, but b is not a dynamic symbol, it's just a symbol because it doesn't change in time. Sympy symbols, and the direction is ax. Now R3, its magnitude is just b, and this vector goes in the bx axis but negative direction because our bx axis is pointing down, but our R3 vector is going up, so it's the opposite direction. And finally R4, that is b in the ax axis. Now if we sum all the vectors R1 plus R2 plus R3 plus R4, we are describing the position of A. Let's see how A looks. That's the description. So we move to the left x in the x hat direction, so we move x to the left, then we move 3b in the ax direction, so we move up 3b, and then we move b to the left on the x hat b vector, so that we arrive here. We confirm that the vector description is correct, and now we can use this equation so that we can relate our variable theta with our variable x and with the position of the point A. Let's look at RA, this expressed in the global reference frame. And you see that this gives us a relation between x and theta on the x-axis and an expression of theta in the y-axis. Remember that RA corresponds to the vector that goes from the origin to the point A, meaning that we are creating this vector as RA. But also RA is the distance from the ground to the point A that we can introduce into our problem as a new dynamic symbol that I will call Y. Let's do Y. It makes more sense with the variables we are using. So the variable Y also describes the vector RA. And it describes the vector RA by doing y times ny. And here you can see that we have an equation. We have a relationship between two vectors. We are describing the position of A going through the red vectors, and we also can describe the same thing going just from the ground to the point by using the new variable y. We can write a different type of expression. We can write an equation where we are making an expression that corresponds to 0, or that it's equal to 0. In that sense, we change our code to make an equation that takes R1, R2, R3, R4, and our definition of RA as a new expression that must be 0. Let's look at equation expressed in N. Observe that the equation must be 0 so that it's describing the same thing as going from the origin, going to A, and then coming back to the same position. So all the components, both the x-axis component and the y-axis component, must be equal to 0. That means that from the first expression, the component in x, we can find an expression that relates theta with x. And from the second one, we can have an expression that relates y with theta.